Hello students, in the last session we completed 19 sums in this chapter, classification of elements and periodicity and its properties. In this session we will do the rest all other questions. So you will get around you get around like 16-17 questions. We'll do all those 16-17 questions in this session. So these questions will also be similar to the question that we have already seen in the last class. So the questions will be based on ionic radii, those arrangements, okay, atomic radius, and then electron gain enthalpy, ionization enthalpy. Then based on the basic acidic strength we'll get questions. Got it? So even in this session the question pattern will be similar to that of the question pattern that we have already seen in the last class. Okay, so all those questions will be super easy. Let's jump into the first question of this session. That's going to be the 20th one. Here the question is, which of the following represents the correct order of increasing electron gain enthalpy with negative signs for the elements oxygen, sulfur, fluorine, and then the chlorine? So here they are given as the four elements and they're asking us to find the increasing order for the electron gain enthalpy. When you look at this electron gain enthalpy, we just know across the period that's gonna increase and down the group it's gonna decrease, right? So only for atomic radius it will be other way around. Then for the ionization enthalpy, electron gain enthalpy, and then the electronegativity, this will be the trend, but you will have some exceptions into it, right? So here they are asking us to find it for these four elements. That's going to be the electron gain enthalpy. We just know in majority of the situation electron gain enthalpy will be like negative, so just do not want to worry about this negative sign. What they're asking us to find is the order based on the magnitude. Okay, so just the normal electron gain enthalpy, that's what I need to find it over here. So we have to get this answer. First I just need to know in what places these elements are present in the periodic table, right? So that's what I need to get. So to get this one, I just know halogens will be towards the extreme right. Before that one you would have got the oxygen family, right? So here you would have got like fluorine and then the chlorine on the extreme right. So before that you would have got oxygen and then the sulfur, right? It has to be clear. When you look at this one, I just know down the group it has to decrease, and then I mean yeah, down the group it has to decrease, across the period it has to increase, right? So if you have to consider it in that fashion, fluorine should have had the maximum electron gain enthalpy, then you should have got the chlorine, right? Because that's obviously has to decrease, right? But I have told you this is one of the exceptions that you need to know with respect to the halogen family. Here in the situation, chlorine would have had maximum electron gain enthalpy when compared to that of the fluorine. Then the arrangement will follow as such, right? So first you would have got chlorine, then you would have got the fluorine, then you would have got yeah, bromine, iodine, and everything. That's gonna follow in the proper fashion. But these two elements, that's gonna swap its places, right? So here it has to be clear. Chlorine would have had maximum electron gain enthalpy when compared to that of the fluorine, right? So this should be done. So then if you look at the elements before it, I have already told you across the period, I just know it's gonna increase, right? Yeah, obviously. But if you look at these two, oxygen and then the sulfur, I just know fluorine and chlorine has to have the maximum electron gain enthalpy. That part is done. When you compare oxygen and then the sulfur, this two will come under the exception category. So down the group, it has to decrease, but sulfur is going to dominate more when compared to that of the oxygen. So it's going to swap its places, right? So first you would have got like sulfur, then you would have got like selenium, tellurium, polonium. Finally, you would have got the oxygen. In the situation, fluorine and chlorine, those two stuff will just get swapped. But with the case of oxygen and then the sulfur, oxygen will be at the very lowest electron gain enthalpy, right? When compared to that of the sulfur, selenium, and tellurium, polonium, and all those stuff. Okay, so you have to be clear with this one. I've already told this arrangement in the theory part, so you gotta be clear. So here you would have got, before this one you would have got this oxygen, yeah, and then before that one you would have got the, I mean sorry, I've made a mistake. So before this one you would have got the sulfur, yeah, and then oxygen would have had the lowest electron gain enthalpy out of all these stuff, so that will be in the very first. Okay, yeah, it should be clear. So when you look at this stuff, it has to be clear. Fluorine and chlorine, as it is towards the extreme right, it has to have the maximum kinetic energy, I mean the maximum electron gain enthalpy. So therefore fluorine and chlorine had the maximum electron gain enthalpy. When compared to this oxygen family. So when you take the oxygen family, the order that we expect is oxygen should have had the maximum electron gain enthalpy, but that's not how it's going to be over there because that's an exception category. Therefore, sulfur will have maximum electron gain enthalpy when compared to that of the oxygen. So oxygen would have had the least electron gain enthalpy, right? So you should be clear with this increasing order that I've told you. Got it? You shouldn't have any doubt on this question. This is easy one. If you're thorough with the theory part, you should get this one straight away. The answer over here is option 2. It has to be clear. Let's move to the next question. Next question is, among the elements calcium, magnesium, phosphorus, chlorine, the order of increasing atomic radii is. So here, just by looking at the elements, I just need to get the increasing order of atomic radii, right? If, with the case of atomic radii, across the period, it has to decrease. Down the group, it has to increase, right? So here, first let me position it based on the periodic table for the elements. So you have got yeah, first you would have got like magnesium, then you should have got calcium, isn't it? So magnesium will come first, and then you would have got like calcium. Next, yeah, it has to be clear. Then with the case of phosphorus and then the chlorine, yeah, it has to be like sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, right? So first you should have got the phosphorus, then you would have got the chlorine, right? In between you would have got sulfur. Do not want to worry about that one. So I just need to get the increasing atomic radii. Across the period, it has to decrease. Down the group, it has to increase, right? So this is in the same period. Therefore, yeah, it has to decrease. Here it is like down the group. Therefore, calcium should have had the maximum atomic radii. Therefore, calcium has to have the maximum. Then you should have got like magnesium. Then across the period, it's going to decrease. Therefore, chlorine would have had the lowest atomic radii, right? So only one option is possible just by figuring out the calcium. That's going to be option 2. Fine. It has to be clear. Simple sum. Let's move to the next one. This question is also easy one. Let me read it. Among the following, which one has the highest cation to anion size ratio, right? So to get this one, so first cation has to be in the numerator and then the anion has to be in the denominator, right? So that's how I'll have to put this one. So cation will be, that's how they are asking us to find the ratio. So cation will be in the numerator and then anion will be in the denominator. And then I have to get the ratio. So which one has the maximum, yeah, cation to anion ratio. See, if you look at the cation, that's going to be positive. Therefore, that will be shorter when compared to that of this anion, right? So to get the maximum value over here, yeah, this value has to be as big as possible. Cation has to be as big as possible. And because you know that's going to be a positive ion. Therefore, once you remove electron, that size is going to shrink, right? Therefore, with the case of cation, to get the maximum cation to anion ratio, the numerator has to be greater as much as possible. With the case of anion, it's going to attract the electron, right? So that's a kind of electron gain. Therefore, with respect to anion, the size is going to increase, right? So I know the size of the anion is going to be greater when compared to its neutral atom, but in this situation, it has to be low when compared to other anion that they have given in the question. Okay, so this is how I just need to take the comparison. So first, let me verify it with the cation. Okay, so you have got like cesium, and then the cesium again same lithium, sodium. So if you just look at this one, this is going to be the first group, right? Sodium, lithium, cesium, all those stuff are the first group. So here I just need to get the biggest cation. So to get the biggest cation, that obviously has to be the cesium, right? So that stuff is done. So cesium, yeah, I just need to get the biggest cation. That's going to be the cesium. Fine. So with the case of iodine, fluorine, fluorine, fluorine. So you got the same fluorine. That's going to be the halogen. So with respect to anion, you should have got the lowest ion, okay, which has the lowest radius. So that's going to be fluorine. I just know down the group that's going to increase. Therefore, iodine wouldn't be possible. Therefore, the answer here is cesium fluoride. Option 2 should be my answer, right? The idea and the logic that I've told you has to be clear. You shouldn't have any doubt in this question. Let's move to the next one. Next question is also a simple one. Let me read the question. Amongst the elements with following electronic configuration, which one of them may have the highest ionization enthalpy? So even in this case, with respect to ionization enthalpy, you get the same order, which is across the period that's gonna increase, and down the group it's going to decrease, right? So if you just look at this options, yeah, it has to be clear. This will be from the third period, right? After neon, you would have got like third period, and this will be argon is the only one. Yeah, it's the only one option which has the fourth period into it. Then if you just look at this 3 and 4, this is same. It's gonna be 3s2 3p1. Here you have got like 3s2 3p3, 3s2 3p2. But only if you look at this one, that's gonna be from the next period, which will be like the fourth period over here. Fine. So here I just need to get the highest ionization enthalpy. As we already know, across the period it has to increase, and down the group it has to decrease, right? So if you just look, just by looking at across the period, you have got 3p1, 3p2, and then a 3p3. Only exception over here is this 3p3, which has like completely filled. Okay, so the completely filled, yeah, 3p3 element over here is the phosphorus. So this will switch its place between the, yeah, it will switch between the sulfur and then the phosphorus, right? You should have got like silicon, phosphorus, sulfur. Instead of that one, you would have got silicon, sulfur, phosphorus, because phosphorus will switch its places, because it has the half filled p shell, right? If they're given you like 3p4, you shouldn't have chosen 3p4. Instead you should choose this 3p3. But here there isn't any confusion, because the option is only between 3p1, 3p2, and 3p3. We just know across the period it has to increase, right? So 3p3 should have had the maximum ionization energy, right? Down the group, what will happen? Down the group it has to decrease. Therefore do not want to worry about this one. Option 2 is obviously not possible. Yeah, the only confusion is between across the period. Even across the period, that's going to be the straight one, because you do not have 3p4 for the confusion. 3p3 will be more stable, therefore removing one electron is going to be tough. Got it? So the answer here is option 4. Got it? Simple one. If you are thorough with the theory, it has to be easy. Let's move on to the next one. This question is also simple one. Arrangement based on the size. Identify the correct order of the size of the following, right? I just need to get the correct order for the ions. So here you should already know that the maximum negative sign will have the highest ionic radii to it. Therefore sulfur should obviously have the maximum ionic radii, so that stuff is done. Then the next, the next element which has the lowest negative sign into it, that's going to be chlorine. Okay, so before sulfur you should have got the chlorine, and that stuff is done. Then before that one you should get this noble gas, right? So here the order will be such that sulfur, chlorine, argon, potassium, calcium, right? So here argon, yeah, that's going to be the neutral species or the noble species over there, so that will be in between. Then I will have to, then I have removed one electron from it, that's going to be the potassium, and before that I have removed two electron, that will be more shrunk, therefore that's going to be Ca2 plus, right? So the order should be such that it starts with the Ca2 plus, which has the positive oxidation state over here, the maximum positive, and then when you go to K plus, that only one electron has been removed, therefore that's going to be a little bit bigger when compared to that of this calcium. So that's how the order will be, right? So here the answer is option 1, right? Simple one, it has to be clear. Let's move to the next question. This question is, with which of the following electronic configuration of an atom has the lowest ionization enthalpy, right? So here also I just need to get the lowest ionization enthalpy. Same way, down the group it has to decrease. I mean, down the group, the ionization enthalpy has to decrease. Across the period, it has to increase, right? So here, if you just look over here, it's like the nitrogen family, right? 2p3. Yeah, that's going to be more stable. So you would have got like 2p3, that's stable. This is going to be across the period, right? So it has to increase. Yeah, then 2p6, this is a noble gas configuration. That too will not work out. Then 2p5. This stuff is actually across the period. So as you move across the period, what will happen? The ionization enthalpy has to increase. Therefore 1, 2, 1, 3, and 4 is not possible. Only stuff that's exception over here is like down the group, which will be this option 2, 1s2, 2s2, 2p6, and then 3s1. Yeah, that's going to be sodium, right? So as you move down, the first one is like 3s1, which will have the lowest ionization enthalpy, because down the group the ionization enthalpy decreases, right? The answer over here is option 2. It has to be clear, simple one. Let's move to the next one. the next question is, which one of the following ionic species has the greatest proton affinity to form a stable compound? Okay, so here what they have given is like proton affinity. That's actually a new term, isn't it? So this proton affinity actually means something that has greater tendency to pull H plus ions towards it, right? So that's gonna have maximum proton affinity into it. Let's say, for example, you just take an you just take an element A, and then it's going to combine with the proton H plus, and then what will it form? It will form like AH plus. Okay, got it. So that's how it's going to be. So this element, what this compound, what it does is it's going to pull the proton, which is the H plus ion in the solution, and then it's going to form the AH plus. Fine. So out of this compound that they have given in the question, which has a greater tendency to pull, which has the greater tendency to pull this H plus ion. That's what I need to get. So that's going to be the proton affinity. Okay. So this is going to be exactly opposite to that of the electron affinity. So electron, with the case of electron affinity, what's going to happen over there is something that has a greater tendency to pull the electron. Okay. But in this situation, this is going to be something that's going to pull the positive charge towards it, right? So yeah, so something which has greater electronegativity will have the lowest electron affinity, I mean proton affinity. Okay, so these two stuff will be oppositely related. So that's the notion that we need to know to solve this question. So electron negativity and then the proton affinity will be oppositely related. So what does electronegativity means? Something that has greater tendency to pull the shared pair of electrons. So within itself, if it has a greater tendency to pull the shared pair of electrons, so obviously it will also be able to pull the electrons from the outside molecule, right? So same thing here. Something that has greater electronegativity will have the lowest proton affinity towards it because that is stable just by pulling the electron itself, right? Got it? Yeah, the idea has to be clear. So here I just need to get which one has the lowest electronegativity, right? So that's what I need to get. So even here also across the period, that's going to increase, down the group that's going to decrease, right? So first let me arrange it. So leave the hydrogen. So nitrogen, fluorine, iodine, sulfur. This is the one that's going to pull the positive charge towards itself. So if you have to place it based on the periodic table, then you would have got like first you would have got oxygen, nitrogen, fluorine, right? So you would have got like nitrogen, then you would have got the fluorine, and below you would have got the iodine, right? Yeah, oxygen, sulfur, right? Nitrogen, oxygen, fluorine. So beneath the oxygen, you would have got the sulfur. So this is how the arrangement is going to be. So we know across the period, it's going to increase. Down the group, it's going to decrease, right? So if you compare this fluorine and then the iodine, fluorine and then the iodine will have the greater proton affinity because it has the lowest electronegativity. But you have got like across the period also. So there isn't any comparison between the nitrogen and the iodine because iodine in itself is halogen. Therefore, obviously that's going to have greater electronegativity. If you just go two step two step ahead of this fluorine iodine, you would have got this nitrogen in the periodic table, right? So here the nitrogen, which has the lowest electron affinity, then obviously it will have the highest proton affinity. So nitrogen will have had the greater tendency to attract this H plus ions, right? When compared to this fluorine, because nitrogen it has to attract that one because when you take the fluorine, it is highly electronegative. Therefore, it is going to be more stable just by pulling the shared pair of electrons towards itself. But when you look at this nitrogen, this will readily accept the H plus ion when compared to that of this fluorine, right? P block elements, nitrogen will have had the maximum proton affinity. So that will be my answer. So the answer over here is NH2 minus, right? NH2 minus. So the answer is option 1, right? So comparing all these four compounds that they've given, the answer is like option 1. So comparing all those four options that they've given, you have got like NH2 minus, F minus, I minus, HS minus. So what that's going to form? So NH2 minus is going to attract this H plus ion and then it will form like NH3. So all these compound or element is going to get into the neutral state. So which one will readily get into the neutral state? So that has the greatest proton affinity, right? So here this NH2 minus will comparatively easily attract that H plus ion when compared to that of fluorine, iodine, and then the HS minus, right? So that's the understanding that you need to know. You shouldn't have any doubt on this question. It has some clear. Let's move on to the next question. Next question is also simple memory based question. Let me read it. Which of the following is the most basic oxide, right? So I have to get the most basic oxide out of the four options that they've given over here. So if you just look at this one, it has to be obvious that majority of these elements are, yeah, all the elements are from the P block elements. Yeah, first let me write that order. If once I get that order, it will be easy. I'll be able to match it straight away. Let me start it with the boron family. So you would have got like packet, right? Boron, aluminum, gallium, indium, and then you would have got like thallium, right? Back boron, aluminum, gallium, indium, thallium. Then after boron, you would have got like carbon, right? So you for the carbon, it's gonna be carbon, silicon, germanium, right? So carbon, silicon, germanium, and then tin lead, right? So that's gonna be tin SN, lead SPB. So this is how it has to be. Then boron, carbon, nitrogen. So then comes the nitrogen family. So you'd have got like nitrogen, and then phosphorus, right? Yeah, nitrogen, phosphorus, AsSBBI. So that's gonna be easy. Arsenic, SbBi. So that's gonna be arsenic, antimony, bismuth. So here you have got germanium, tin lead. Okay, you should have memorized this one. It has to be by heart. So here I just know, if you remember that one, the oxides that I've given for you in the theory part, if you have memorized that chart, you should be able to get this one. Towards the extreme right, you would have got like, yeah, basic oxides. Towards the right, towards the left, you would have got the basic oxides, and towards the right, you would have got the acidic oxides. In between, there will be like amphoteric, right? So here, what they're asking us to find is the most basic. So which one has the most basic nature into it? I just know, same way across the period, acidic nature increases, down the group, acidic nature decreases, right? So first, let me find out the amphoteric oxide. If we have to get the amphoteric oxides, aluminum, gallium, that's going to be amphoteric. Same way, germanium, tin lead, that's going to be amphoteric. Same way, arsenic to bismuth, this is going to be amphoteric. So these elements are acidic in nature. These two are basic in nature, right? So what they're asking us to find is the most basic one. Have you got any options related to indium and thallium? Let me look it. You do not have indium and thallium into it. So what you have is this selenium. Yeah, that's not possible because that's going to be acidic. Selenium, tellurium, polonium. Okay, that's going to be for the oxygen sulfur. So that's obviously acidic in nature. What they're asking us to find is the most basic one. So that's going to be acidic. Then if you compare the aluminum, that's amphoteric. Okay, then SBBI, right? So SBBI. So when you compare these elements, as you move down the group, I have already told you, across the period acidic nature increases, down the group the acidic nature decreases, right? So across the period the acidic nature increases. Therefore, if you compare SB and then the BA, I just know this is the only stuff that is down the group. Therefore, BA should have the lowest acidic nature, which means it should have the maximum basic nature, right? So those two stuff will be oppositely related, right? So if they have given you the comparison between the lead and then the bismuth, lead would have got the most basic oxide in the situation, but here there wasn't any comparison between these two series. The only group that they have given us the nitrogen family. When you compare that nitrogen family, that's going to be SB and then the BA. I just know down the group the acidic nature decreases, which means the for the bismuth you would have got the maximum basic nature into it. Therefore the answer over here is BI2O3. Option 4 will be my answer. See, if you are thorough with the theory part and all those chart, if you have memorized it very well, these are like easy questions, you'll be able to do it straight away, right? There isn't much thinking into it. Only thing is you should have memorized those chart that I've given you, right? It has to be clear. Let's move to the next one. This question is a little bit tricky. Let me read the question. What they've given over here is, what is the correct relationship between the pH of isomolar solution of sodium oxide? So they've given you some compounds. That's going to be sodium oxide, sodium sulfide, sodium selenide, and then the sodium telluride. Okay. So they've given you like 4 different compounds, and they're asking us to find the pH of its isomolar solution. Fine. So when you look at these compounds, sodium is the one that's going to be constant for all those compounds. But if you look at the oxygen, so oxygen, sulfur, selenium, telluride, so these stuff are going to change. Okay, so I wouldn't be able to match it with the oxides that we have learned, that chart. Okay, because in that situation, if that was the case, they should have given us like O2, SO2, okay, something like that, SeO2 or SeO3. If they've given you in that fashion, then oxygen would be constant. What is going to change over there is the cation. But in the situation, the sodium is constant, but what is changing over here is the oxygen sulfur. So the oxygen anion is changing over here, right? So I shouldn't compare this one with the oxides that we have learned, that order. Instead, I'll be able to compare it with the hydrates that we have learned. Okay, so in the case of hydrates, I know, yeah, across the period it's going to increase, down the group it's going to increase. So even in both those situations, that's going to increase, right? So I can match it straight away with the hydrates, because the sodium has the valency 1, same way hydrogen also has the valency 1. If it was like H2O, when H2O splits, that's going to split as H plus and then the OH minus ions, or else H plus, 2H plus, and then O2, O2 minus, right? So that's how it's going to split. Same way, even if in the situation, if it is going to split, that will split as like Na plus and then the O2 minus. So that's how it's going to split even in the situation. Therefore, I can match it with the hydrates pattern. Okay, so with the case of hydrates, that order, even across the period it's going to increase, same way down the period, I mean across the period it's going to increase, same way down the group it's going to increase, right? So same analogous situation, I'll be able to fit it over here, right? So if they given you like H2O, H2S, H2Se, it would have been easy for us to match it with the hydrates. In this situation also, I'll have to match it with the hydrate, because sodium is also monovalent, same way, and it is positive, same way sodium, hydrogen is also monovalent and it is a positive cation, right? So I can match it with the hydrate series. It has to be clear. And so what would happen? So if you consider it in this fashion, from oxygen, it goes still up to like tellurium, right? So it starts from the oxygen and goes up to like tellurium. I know down the, yeah, like down the group, acidic nature increases. Therefore, if you compare over here, the acidic nature of tellurium is going to be greater. The acidic nature of oxygen with respect to hydrate is going to be less, right? So here, this has the maximum acidic nature. Something that has more acidic nature to it will have less pH value, right? So if the pH value is less than 7, that's going to be acidic. Same way, if pH value has to be less, then its acidic character has to be more. So if I have to compare between the oxygen and then the tellurium in the situation, I obviously know tellurium has the more acidic nature to it, so it will have the lowest pH. It will have the value to be less. If I consider the oxygen that has less acidic nature to it, which means it is more basic, so the pH value will be greater, right? If the value is greater than 7, that's going to be more basic. If the value in the pH scale is going to be less than 7, that's going to be more acidic. So if I compare it in this fashion, oxygen, which has, when in comparing in this series, oxygen should have had the more pH value, because it is more acidic it is more basic in nature, right? You should have got this understanding. So to solve this sum, I'll have to match this entire series with the hydrate series. If I do match it with the hydrate series, I'll get the answer straight away, right? So here you would have got like pH1, which has to be greater. Yeah, then you should have got like pH2, pH3, pH4, right? Obviously, either it could be 1 or 3, because approximately equal to isn't something that is possible for me to find, but it should be clear. One should be my answer, right? The other one, option 3, is exactly opposite, so that cannot be my answer. So option 1 will be my answer. Fine. So what, see here, if you just look at this question, what they given over here is the Na2O, right? So they have given here Na2O. See these compounds, Na2O, Na2S, this is like alkali metal, it's going to react with the oxygen. So when these two stuff are going to react, that's going to produce crystal. Okay, NaCl, that's a common salt which is going to be like crystal. Same way, when some positive element or the metal atom, when it reacts with the anion, it will just form crystal. Okay, so here also Na2O, Na2S, whatever it is, Na2Se, all those elements are actually crystalline nature. So when this Na2O is mixed with the solution, so what is going to be my solution? Generally, universal solvent is going to be water. So when it reacts with water, what will it form? When it reacts with H2O, it will form 2NaOH in the situation. So once you dissolve this crystal into the water, that's going to produce like 2NaOH, right? Fine. So this is how the reaction is going to be. You do not want to worry about this reaction. Oh, see, what I intend to tell you over here is when this two stuff is going to mix, it will obviously produce this base. Okay. So when it is going to produce base, so what I'm supposed to find over here is which one is more basic. That's what I need to find it over here. So to get this value, I can easily match it with the hydrates to get the answer, right? So that is how we are going to do it. That's how we are supposed to solve this up, right? Yeah, you shouldn't have any doubt in this question. Once you are thorough with those series, hydrate series, and all those stuff that I've told you in the theory, this will be super easy for us to solve, right? Yeah, it has to be clear. Little bit tricky, Sam. You have to be clear with this question. Let's move to the next one. Next question is simple statement based question. Here you have got ionic radii, or yeah, I'll have to match it straight away with the statement inversely proportional to the effective nuclear charge. Yeah, that's the answer, because if the effective nuclear charge is greater, it's gonna pull the outer electron. Therefore, the ionic radii will become shorter. So more the effective nuclear charge, then obviously ionic radii will be less. So those two stuff are oppositely related. Therefore, it has to be inversely proportional to. Option 1 should be my answer. Let me read first three other options. Inversely proportional to the square of effective nuclear charge. That doesn't make sense because it is just inversely proportional. That's it. Directly proportional and directly proportional. That wouldn't be my answer, right? Simple, straightforward sum. Let's move to the next one. Next question is also simple one. Yeah, we have already seen the order in the previous sums. They have asked the same question based on the statements. Here the question is the ions O2 minus, F minus in A plus, Mg2 plus and Al3 plus are isoelectronic. So they have given you like 5 elements and they have told you that those are isoelectronic. Their ionic radius show. What pattern does that ionic radius show? So yeah, obviously O2 minus should have had the maximum ionic radius, Al3 plus should have had the least one. So if that's going to be the case, a significant decrease from O2 minus to Al3 plus, that has to be my answer, right? Rest all other option doesn't make any sense. It has to be clear. Option 2 is my answer. Let's move to the next one. This question is also based on the order. Let me read the question. Which of the following order is wrong? So I just need to get the wrong order. First one is like NH3, pH3 and ASH3. So the order is based on acidic nature. Here it's like hydrate. Therefore, as you move down the group, acidic nature increases. So first one is right. So that's not going to be my answer. Then they're asking us to find the first ionization potential or ionization enthalpy. So if I have to get that one, lithium, beryllium, boron, carbon. See, I just know this beryllium is actually 1s2. It's like fully filled as subshell or orbital. Therefore, so these two has to switch its places. So it should have been like lithium, boron, beryllium, carbon here. That's not how they have given us. So that's going to be the wrong. So option 2 is the wrong one. Let me verify 3 and 4 and then let's move to the next question. So here they're asking us to find the basic order, okay? Basic nature based on the order that they have given over here. So if you have to get that one, obviously this one has to be right. Anyway, these are like oxides. It's not hydrate, these are like oxides. So with the case of oxides, across the period, it has to increase acidic nature. Down the group, it has to decrease, right? So first, let me arrange it based on the position in the periodic table. If I have to do it, you'd have got like sodium, potassium, isn't it? So sodium, and then you would have got the potassium underneath it. So after sodium, you would have got like magnesium, sodium, magnesium, aluminum, right? Sodium, magnesium, and then you would have got the aluminum. Yeah, if you have to compare this one, acidic nature increases, right? Acidic nature decreases. So this one has to have the lowest acidic nature, right? Which means it will have the more basic nature into it. Therefore, sodium has more basic nature. Then comes the magnesium, and then comes the aluminum. Okay, so if I have to compare it with the basic nature, sodium will have the maximum basic nature to it. Then you would have got the magnesium and then the aluminum because it's opposite to that of the acidic nature. Yeah. Then down the group, acidic nature decreases. Then basic nature has to be more. Therefore, K2O will be at the very last position, right? This one has to be clear. Yeah. Then finally, you have got the ionic radius. If I have to compare the ionic radius, it's like lithium, sodium, potassium, rubidium, cesium. I'm just moving down the group. Therefore, as you move down the group for the same element, the atomic radius or ionic radius is going to be greater, right? So lithium should have the lowest, cesium should have the greatest in this condition. Therefore, 1, 3 and 4, both those three options are right. The wrong answer is like the option 2 with respect to the ionization potential, right? It has to be clear. Let's move to the next question. This question is also a simple one based on the ionization potential, same as that of the previous sums that we have already done. Correct order of first ionization potential among the following elements: beryllium, boron, carbon, nitrogen, oxygen. Okay, so that's the exception, we know, right? So beryllium should be after that of the boron. So you'd have got like boron, beryllium. Yeah, boron, beryllium. Either it could be like option 1 or option 2, boron, beryllium. Then carbon, oxygen, nitrogen, right? Because nitrogen will have like half-filled p shell, which will be preferred. Therefore, the answer here is option 1. It has to be clear. Right, let's move to the next one. This question is statement based question. The question is statement 1: acid strength increases in the given order as HF, HCl, HBr, HI. I know with the case of hydrides, as you move down the group, it's gonna increase, fine. The explanation that they've given as is as the size of the element F, Cl, Br, I increases down the group, the bond strength. Yeah, see, we'll learn this one more clearly in the next chapter. As if now, here fluorine is going to be, yeah, here when while comparing fluorine, chlorine, bromine, iodine is going to be much more bigger when compared to the death of fluorine. It's going to combine with the same hydrogen atom, right? Therefore the bond length between hydrogen and then the iodine, okay, will be greater when compared to that of the bond between hydrogen and then the fluorine, because fluorine is shorter, therefore the bond length is going to be less. So if the bond length is less, it's going to be hard for me to break. Okay, so that's what they would have given over here. The bond strength of HF, HCl, HBr, HI decreases because as you move down, the distance between the nucleus of the hydrogen and the iodine is going to be greater. So when it is greater, it is easy for me to break. So more the bond length, less the bond strength. Fine. Yeah, we will learn bond length and bond strength more clearly in the next chapter. So this basic understanding has to be clear as if now. The bond strength of HF, HCl, HBr, HI decreases. Yeah, the bond strength decreases because the length between the iodine and the hydrogen is going to be greater. Therefore, it will be easy for me to break. And so the acidic strength increases, right? Yeah, you should clearly know this idea. Yes, so obviously that has to be the correct statement because that's the reason. As it is easy for me to break this hydrogen and then the iodine, I'll be able to produce more amount of stable H plus ion, which will be ready to react with the base. Right? So the acidic strength increases. So that's the logic. So the logic in itself is correct. So obviously what they're asking is to find is in the light of the above statements, choose the correct answer from the options given below. Both statement 1 and 2 are false. That doesn't make sense. Statement 1 is correct, whatever it is. I just know both the statements are right. So that should be my answer. So both statement 1 and statement 2 are true. So the answer here is option 4, right? You have to be clear with this one. Yeah, no doubt should be there. Let's move to the next one. Next question is also a simple one. From the following pairs of ions, which one is not an isoelectronic pair? So I just need to get something that is not isoelectronic, which means it doesn't have same count of electrons into it. Na plus and then the Mg2 plus. After Na, you would have got like magnesium. So removing one electron, removing two electron will produce isoelectronic species. Therefore, this is isoelectronic pair. Therefore, this is not my answer. Fine. Then you have got like Mn2 plus and then the Fe3 plus. Yeah, scandium, titanium, vanadium, chromium, manganese, iron. Okay, so with the case of manganese, I've removed two electrons, and then the iron comes next to the manganese, and with the case of iron, I have removed three electrons. So obviously, these two are isoelectronic. So therefore, that shouldn't also be my answer. Then Fe2 plus and Mn2 plus. So obviously, this should be my answer, right? These are not isoelectronic pair because I've already explained the reason in the option 2. Therefore, option 3 will not be isoelectronic pair. So that will be my answer. If you consider O2 minus and then the F minus, that produces noble gas configuration. Both will have the same electrons into it, right? So it has to be clear. Simple one. Let's move to the next question. The next question is the IUPAC name of an element with atomic number 119. So I have to get the IUPAC name for this element 119. So for 1, that's going to be N. So N, NEM, right? For 9, that's going to be EN. So that's NEM. Fine, if you're clear with the IUPAC nomenclature that we have seen in the theory part, this one is like super easy, right? Let's move to the next one. This question is also simple, straightforward one. The element expected to form largest ion to achieve the nearest noble gas configuration is. So, to achieve the nearest noble gas configuration, which will have the largest ion, that's what I need to get over here. So, here it has to be the neon, right? Yes. So you have to remove one electron. So if you remove one electron, it's going to become positive. So in that's Na plus. So obviously that's going to shrink. Yeah, what they're asking is to find is the largest ion. So Na plus wouldn't make any sense. Then you have got like O2 minus, F minus, and N3 minus. Something that has more electrons into it will have the largest ion, right? So obviously option 4 has to be my answer. Simple one. Same kind of sums that we have already seen, right? It has to be clear. No doubt should be there with all the sums that we have seen. So in this session, we have done around like 18 sums. So all those sums felt like simple, straightforward ones. Some of the sums felt a little bit complicated and a little bit tricky. Yeah, if you have that intuition and the cross thinking, we'll be able to do all those sums also, right? So this is one of the easiest chapters in the chemistry, right? If you're thorough with the theory part, just by looking at the question, we'll be able to get the answer. But the point is, you have to be extremely thorough in the theory part, right? All those orders and everything, you should have memorized it completely. Only if you know those by heart, we'll be able to solve the sums quick, right? Fine. So with this, all the questions that were related to this chapter, classification of elements and periodicity and its property, got completed. Got it? Until 2023, we have done all those questions. Fine.